Hello, welcome to the first video concerning projectile motion. And this is a fun topic because we're going to talk about projectiles. What are projectiles anyway? They are simply objects launched into the air that are subject to gravity. That's what a projectile is. So projectile motion is interesting because we're going to look at how we can find the displacement, the velocity, and the acceleration of a projectile at different points in time. We're going to look at the pattern to the path of a projectile. They have a pattern, in case you didn't know. We're going to ask ourselves this question: do the horizontal and vertical components affect each other when we're talking about projectile motion? We're talking about horizontal and vertical motion, the components of velocity or of a particular motion, and do those affect each other? How can we calculate the displacement or initial horizontal velocity for a projectile launched horizontally? So I'm going to show you how we can calculate that as well. So first, let's look at that first question about displacement, velocity, and acceleration of a projectile. And why is it interesting or any different than any other problem? Well, if you look at, or just think about, let's look at this little cannon here. It's launching, boom, directly horizontally. Its initial velocity is 20 meters per second in that horizontal direction. And if you'll notice, as the little ball or cannon or whatever we have here, this projectile is traveling along, we have a horizontal velocity, but we also have a vertical velocity, and we also have acceleration due to gravity. That is not in the same direction either. We have, if we add these two vectors together, we're going to get some little arrow in between those going this direction and gradually changing direction as it goes. Our acceleration is always pointing down. It's pointing in a different direction than the velocity. The displacement is pointing in a different direction from the acceleration as well. So when we're talking about projectiles, the velocity, the acceleration, and the displacement do not all point in the same direction. So that makes the problem a little more complicated and a little more interesting. Is there a pattern to the path of a projectile? Yes, there is indeed a pattern. It's called a parabola, and you all know that from math. Just a little review that a parabola is a curve. Here's a parabola. It's the curve. Every point on that curve is the same distance from a fixed point, right here, a focus, right there. It's the same distance from there as it is from what is called the directrix, a fixed line. That is the line out here. So if we draw that fixed line here and that focus here, every point here on this parabola would be equidistant from the focus to the directrix. That's the mathematical definition of a parabola. Here are just some lovely pictures of parabolas, right here and right here, and obviously they would be vary from one to the next depending on a lot of factors involved in that projectile. Does air resistance affect the path? Yes, indeed it does. So when we do our calculations, we're going to assume negligible air resistance when we do our math. So here's a cute little picture, basically contrasting free fall and projectile motion. Free fall, the woman is simply demonstrating free fall. The man is demonstrating projectile motion. Projectile motion is essentially free fall with some initial horizontal velocity. And since the air resistance is being considered to be negligible, that horizontal velocity remains the same throughout the path or the trajectory of that projectile. And you remember that from the previous slide where the horizontal velocity remained constant throughout. The vertical velocity does not. it is being affected by gravity, and it's accelerating. So the vertical velocity does not, but the horizontal velocity remains the same. Again, do the horizontal and vertical components affect each other? Look at this picture here where we have a free fall and we have a projectile. The object that is showing projectile motion, if you were to be able to draw a line between these, this will hit the floor at the same time that this hits the floor. Their vertical components are exhibiting the same behaviors here. So we have here, 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 here. The vertical component does not affect the horizontal component. Just because it is going horizontally this way does not mean that it will slow down for some reason as it travels down to the ground. They will both hit the ground at the same time. Keep in mind, once again, this is negating air resistance. If we're talking about really long-term scenarios where air resistance does need to be considered, they probably wouldn't hit the ground at the same time because of the air resistance. So here are some wonderful formulas that are going to help us calculate motion of projectiles. We're going to consider, the first type of projectile will be one that falls from rest, a free fall. And when we talk about this free fall, where it's falling from an initial velocity of 0 or from rest, it's a special type of projectile. It doesn't have any horizontal velocity. And for this, our formulas actually are pretty simple. We're going to go back and remember all those wonderful kinematic formulas that we learned last unit. I wrote some of them down right here so that we can look at them. This one right here, velocity with constant uniform acceleration, we're going to apply this because we know that if we start in this free fall, if we start with this initial velocity of 0, then we can simply rewrite this equation, because if we know this is 0, we're just going to use this portion of the equation, then acceleration times change in time. Well, in free fall, the acceleration is acceleration due to gravity, so we can just call it a little g. And acceleration due to gravity, since it's going this direction, down, it's going to be negative. So we get this formula. The velocity in the vertical direction, this up and down direction, final, is going to be equal to negative g, acceleration due to gravity, 9.81 meters per second squared, times change in time. That's where that formula comes from. Again, the second formula is very similar. We're looking at this formula from our kinematic expressions, the final velocity after any displacement. We have v squared equals final equals v squared initial plus 2a times the displacement. Now this is delta x because we weren't talking about, we were just talking about one-dimensional motion. We're now talking about two-dimensional motion, and we're talking about the dimension, up and down dimension, the vertical dimension. We're calling it delta y. This just represented in any direction. So we're going to change that into our delta y because we're talking about this vertical up and down direction. And again, our initial velocity is going to be 0 meters per second. So we can ignore that term when we transfer this equation into this equation that is going to apply to our projectile falling from rest. Again, we're going to substitute acceleration due to gravity, and it will be negative because it's always down. It's going down. The acceleration due to gravity is in the negative direction. So here's where we get that equation. And third, I actually wrote the wrong equation, or typed the wrong equation in here. There are two: displacement with constant uniform acceleration. This is the one we're interested in, not that one. And this is the one we use to derive this equation. Again, delta x is simply referring to any displacement in any direction in just a one-dimensional coordinate system. This is actually, it has two dimensions to it, what we're talking about here, and we want only the vertical, the up and down direction. So we're going to call it delta y, because we're now very concerned with which direction we're going, and we want it to be up and down. So it'll be delta y, and this term here is going to be 0, because the initial velocity is 0 meters per second. So that term is going to be 0. We can simply look at this term. A, again, is going to be acceleration due to gravity, and it's in the down direction, so it will be a negative g. So we get our negative g, and then the 1/2 as well, and we can maintain our delta t squared. So that is where this equation comes from. Now let's look at our horizontal velocity. Remember that in physics we get to simplify and assume things like negligible air resistance. We're not going to take that into account. Therefore, our horizontal velocity can be assumed to remain basically constant. And that is where we get this idea, right? The velocity in the horizontal direction, it's going to be a constant. So whatever our initial velocity is what our velocity is. It's remaining a constant. They're the same. Now, this second equation, that one comes from this kinematic expression that we learned last unit for average velocity. Average velocity is equal to the change in displacement over the change in time. And we're just simply going to apply that to our horizontal direction. If I multiply both sides of this equation right here, if I multiply both sides by delta t, I end up with delta x, and the delta t's cancel, is equal to average velocity times delta t, which is this expression right here. Delta x equals the velocity, average velocity in the horizontal direction, times delta t. Now you know where all these formulas come from. You don't have to be afraid of where they came from. If you find yourself lost somewhere with no way to access important physics equations, you can derive these all on your own. Let's work through an example together. All right, well, people in movies often jump from buildings into pools. It's just fine and interesting. Don't ever try that at home. Let's say a person does jump from the 10th floor, and we're going to assume that to be 30.0 meters, into a pool that is 5 meters away from the building. With what initial horizontal velocity must that person jump? Here's our little simple steps that we'll follow pretty much most of the time when we're looking at physics problems. Always define, sketch, label, draw a picture, label what you know, write down what you know, write down what you're looking for and what you need to know. Then we're going to choose our equations, we'll calculate them, and evaluate and make sure it makes sense. So let's start with define, sketch, label. Important part of the problem. Here's our little person up at the top. This person's going to jump off into hopefully into the water, right? We know that we have a delta x here of 5.0 meters before we get to the water. We also know that our delta y here equals negative 30.0 meters. He's going down. We also know something else. We know acceleration due to gravity is 9.81 meters per second squared. And what we don't know and what we'd like to know is the initial velocity. So here I rewrote our define, sketch, label portion for you. And let's look at step 2, choose the equations. Now this is something you may want to just write down. For this type of problem, these two equations work really well and they're very useful. And as we work through this, you'll see and you'll have a chance to practice and use them over and over again. So these are the equations, the two equations we're going to use. Let me explain why they're useful. Okay, first you probably are asking yourself, okay, this equation's interesting. I know my delta x. I know my horizontal, change in horizontal displacement here, right? 5.0 meters. I would like to know the velocity, the horizontal velocity? I don't know that. That's a big question mark right here. Remember, it's constant, so whatever it is at a given time, it will be what it is initially. I also don't know change in time. They never told me that in the problem. So I have two variables. That's not good. You're right, that's not good. We need to solve for delta t so that we're able to find that velocity. And this is where this second equation comes in. The second equation is useful because I do know my change in vertical displacement. It's negative 30 meters. I know g, 9.81 meters per second squared. Sorry about that. I had a little dyslexic moment. It's negative 9.81 meters per second squared. I know that. And therefore, I only have one variable, and I can easily solve for time there. Since I know the time that it takes for an object to fall from here to here, that's all the time it has, right? So in that amount of time, that is all the amount of time it has to travel this way as well before it hits the bottom. So I can plug that time into my equation here and solve for my velocity. Okay, now we can calculate, and I apologize again for my dyslexic things here. 9.81. Now, I want to point out something. If acceleration due to gravity is negative g, it's in a negative direction, 9.81, that is factored into these equations. So when I write g, g is simply 9.81 meters per second squared, and this equation has already taken into account that it is in the negative direction here. So when I substitute these values in, I'm going to go ahead and solve for delta t. I'm going to plug in my delta y value here is negative 30 meters, and then I'm just copying this down, and g is 9.81 meters per second squared, and then delta t is here. I'm doing this kind of backwards for those of you who like to plug things in and then chug away at the algebra with actual numbers instead of variables. You can do it either way. If I multiply both sides by a negative number, both sides become positive, and I multiply both sides by 2. Then after that, I divide both sides by 9.81. I end up with a delta t squared equal to this number, seconds squared. If I take the square root of both sides at this point, take the square root, I end up with a delta t equals plus or minus 2.47 seconds. In this case, it's obviously a positive number, 2.47 seconds. I can then plug that value into my second equation. And when I do that, I know delta x is equal to 5 meters. I know my delta t now is 2.47 seconds, and I can find that horizontal velocity. I do that by dividing both sides by 2.47 seconds, and I get a velocity equal to 2.0 meters per second. Now I need to evaluate my work. Does this make sense? One thing I can do is do a quick approximation. I know that 5.0 meters is my delta x. That's pretty 5. I know that my time is about 2.5. I can simply plug some values in here as well and see I can approximate g as 10 approximately. And if I put a 10 in here in my head, I can do a quick approximation, a negative 30 here, and come out with about 2.5 seconds. Plug that in, and does that make sense? If I divide 5 divided by 2.5, is that about 2? It actually is. It comes out to be 2. So I can go back and basically round my numbers to something convenient and run through the calculations, make sure that that's in the realm of being reasonable for an answer. So let's review. Obviously, we use components when we evaluate projectile motion. We know that projectiles travel in parabolas, unless, of course, they're just in a plain old free fall. Projectile motion can be described using both vertical and horizontal components. We break it down into components. Here are the equations for our vertical motion when the projectile is simply falling from rest. These are equations for the horizontal motion of a projectile if we have some horizontal motion. And these are the very useful equations that we can use when we're going to calculate displacement or initial horizontal velocity for projectiles launched horizontally. We can use these we know these are both unknowns to us. We can use this as long as we know this displacement to help us determine the time and then the velocity. We can also rearrange these differently if we're given different information in the problem. We can use both of these equations to our advantage in whatever way we need to determine an unknown, and then be able to use that unknown to help us unravel the other portion of the problem. So you guys are going to have some practice that you'll get to do in class. If you are interested in advanced ideas, make up your own problems about horizontally launched projectiles and solve them. I look forward to seeing you in class.